Good afternoon, all. Welcome to the lecture of complex analysis. I'm audible.
Yes, sir.
Okay. So in last lecture we have seen what is a annulus, and there is one theorem. That one is nothing but Casorati-Weierstrass theorem. What is the Casorati-Weierstrass theorem? Yes. What
If
is
given singularity is an essential singularity, then then annulus of that annulus will be exactly approaches to any complex number.
annulus or f of annulus?
F of annulus
Yes, that is any complex number is either a point of that set, that is f of annulus of a0 delta, or
or
it is a
limit
limit point
point
of
of
that one. Okay, that one is nothing but f of that is it is a dense in C. It means f of annulus of a0 delta closure will be equal to C, and that one is nothing but our Casorati-Weierstrass theorem. Now there is a one point which is nothing but the Laurent series development. Okay, first here Laurent series development. First, let us see the statement. If the function f is analytic in, if f is analytic in annulus of point A with radius r1 and r2, where r1 is greater than 0, which is less than r2, and r2 is finite, then f of z is nothing but series n running from minus infinity to plus infinity an z minus a to the power n, where the convergence is absolutely and uniformly, and uniformly in annulus of a point A with radius r1 and r2, where small r1 is greater than capital R1, which is less than r2, which is less than capital R, and also coefficients a and r given by an is equal to 1 upon 2 pi r integral over the curve gamma f of w divided by w minus a to the power n plus 1 dw, or if we take 1 upon 2 pi instead of w, if we use z, then it is nothing but f of z divided by z minus a to the power n plus 1 dz, where gamma is a circle that is mod z minus a equal to some radius r for some r, and this r lies between r1 and r2, and then we have to prove that this series will be unique. Moreover, the series is unique. First, we have to prove that if there is a function here which is analytic in this annulus of A with radius r1 and r2, then f of z is nothing but this one, that is summation n running from infinity to infinity a n z minus a to the power n, where a n is nothing but 1 upon 2 pi integral over the curve gamma f of w divided by w minus e to the power n plus 1 dw, where gamma is a circle, that is modulus of z minus a will be equal to r. That one is nothing but a circle with center at a and having radius will be r, and then we have to prove that this series will be unique. Okay, that is if we will take one another series, that is say your pop is nothing but series n running from minus infinity to infinity, bn z minus a to the power n, then we have to prove that this an and bn are same. Then only the corresponding series, then only we say that the corresponding series is unique. Okay, so first we will prove this one, that is f of z is equal to series n running from minus infinity to infinity, an z minus a to the power n, where an is nothing but 1 upon 2 pi I integral over the curve gamma f of w divided by w minus e to the power n plus 1 dw. Okay, so prove. First, take whatever we have given. F is analytic in annulus of P with radius R1 and R2. It means its center will be some point E. Let us suppose that somewhere here is point E. Okay, this will be some R1. Okay, okay. So this will be small R1. Here somewhere is our R2. Okay, so this will be a, sorry, here we will take first, since annulus of capital R1, this will be capital R2, this will be R1, and small R1 and R2 are lies between capital R1 and R2. So somewhere here this will be our small R1, that is a center circle having center will be A and radius will be small R1. Now R2 is less than R2, so take R2 somewhere here. Okay, so this will be a small R. These things we have given. Okay, now given that F is analytic in annulus of A R1 R2. Let us take R1 and R2 be any two numbers for which R capital R1 is less than small R1, small R1 is less than small R2, and which is less than capital R2. So select first F is analytic in annulus of A with capital R1 and R. Now select two integers small r1 and r2, such that r1 is less than the small r1, which is less than small r2, and which is less than capital R. Okay, let gamma 1 and gamma 2 be any two circles. Yes,
काहींना जॉईन होता येत नाही.
join करायचं. Okay, so select the two circles gamma 1 and gamma 2. The two circles, okay, that is gamma 1 and gamma 2, the two circles having radius will be small r1 and small r2. That is modulus of z minus a is equal to small r1 and modulus of z minus a equal to small r2. Okay, now, and these are in annulus of a with capital R1 and R2. So they are in annulus of a point A with radius R1 and R. Okay, now let us take Z be the any point in this annulus of A with small r1 and r2. Let Z be the point in annulus of A with small r1 and r2. Okay, that is somewhere here. Annulus of A with r1 and r2. This will be a circle with radius r1. This will be a circle with radius r2. So somewhere here is our point Z. That is somewhere here is point Z. And choose a line segment and choose a line segment lambda from a point on circle gamma 1 and gamma 2, and Z does not lies on that line segment, does not lie so on that line segment lambda. Okay, so here we have to take one line segment from a points on circle gamma 1 to circle gamma 2. This will be a circle gamma 1 having radius will be r1, that is somewhere here, this point. Take this one as some, here somewhere is our point. Take this one as some z1, and the point on this circle, that is somewhere here, is a point z2, and this z1 to z2 is nothing but some lambda, and z is not a point on this lambda. Okay, so it means z is in between these two circles and it is not lie on this lambda. Okay, now as a z is a point which is in between these two circles and which is not present on this line segment lambda, then what is the index of a curve gamma 1 with respect to a point z, and what is the index of a curve gamma 2 with respect to a point z?
0.
Both, or index of a curve gamma 1 with respect to point z will be 0 or non-zero?
0.
0. And what about this one? Index of a curve gamma 2 with respect to point z?
0.
अरे इंडेक्सच्या डेफिनेशन नुसार हा माझा कर्व आहे ना, हा काय आहे, माझा गॅमा 2 आहे कर्व, ज्याची रेडियस r2 आहे. झेड हा पॉइंट त्याच्यामध्ये आहे बाय द
1.
डेफिनेशन ऑफ इंडेक्स विच इज इक्वल टू 1. So index of a curve gamma 1 with respect to point z will be equal to 0, and index of a curve gamma 2 with respect to a point z will be equal to 1. So let us take our gamma as total gamma is nothing but some gamma 2 minus of this lambda plus, sorry, minus gamma 1 plus lambda. It means here we have taken curve the circle gamma as this circle gamma 2 minus of this circle gamma 1 with this minus of lambda plus lambda, which is a same. That is actually it is nothing but some gamma 2 minus gamma 1. Okay, now as here we have given f is analytic in this region, that is a annulus of a with r1 and r2. Okay, as it is analytic in this region, then by the Cauchy's integral formula, what is f of z then? F is analytic in this region, annulus of a with r1 and r2, then by Cauchy's integral formula. What is f of z? Which is nothing but 1 upon 2 pi I integral over the curve gamma f of w divided by w minus of z dw. Since f is analytic
Yes,
in
sir.
this region, it means f of z is nothing but this one, 1 upon 2 pi I integral over the curve gamma f of w divided by w minus z dw. So here 1 upon 2 pi. What is gamma? Gamma is nothing but gamma 2 minus of lambda plus lambda minus of, or minus of gamma 1 plus lambda, minus of gamma 1 plus lambda. This will be a circle. Okay, gamma 2 and gamma 1 are the two circles divided by f of w divided by w minus of z dw. Okay, so actually it is nothing but it is equal to 1 upon 2 pi I into bracket integral over the curve gamma 2 f of w divided by w minus of z dw minus of integration over the line segment lambda. That is, take this lambda as some z1 to z2 in f of w divided by w minus of z dw minus of integral over the curve gamma 1 f of w divided by w minus of z dw and plus integral over the lambda, that is z1 to z2 f of w divided by w minus of z dw. Okay. Now, whatever will be the line segment joining point Z1 to Z2, as we, if we find out the distance from Z1 to Z2 or Z2 to Z1, both are the same thing. Okay, so distance is always positive. So this one and this one get cancelled. So here we get 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus of z dw minus of 1 upon 2 pi I integral over the curve gamma 1 f of w divided by w minus of z dw. This first part will be taken as some f1 object and second will be as some f2 object. So which is nothing but f1 object plus f2 object, and total this one is nothing but f of z. Where f of f2 object is nothing but where f2 of z is nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus of z dw, and f1 of z is nothing but 1 upon 2 pi I, sorry, minus of 1 upon 2 pi I integral over the curve gamma 1 f of w divided by w minus of z dw. Okay, so up to now, any doubt?
No, sir.
Okay. So let us take consider here we will solve this f2 object. So consider f2 of z, and f2 of z is nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus of z dw. So which is actually nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by, this w minus z can be written as, if here somewhere, that is in this term, if we add plus a and minus a, then this will be same. Since here we will add some finite quantity, that is plus b. Okay, so this can be written as w minus of a plus a minus of z dw, which is nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by this w minus a as it is. Here take this minus common, then it becomes z minus of a dw. Now take the w minus a common from denominator, then it becomes 1 upon 2 pi I integral over the curve gamma to. If we take w minus a common, then it becomes 1 minus z minus of a divided by w minus of a into dw. Actually it is nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus of a into 1 minus z minus a divided by w minus a inverse of dw. But we know that what is 1 minus z minus a upon w minus a to the power minus 1? Somewhere we have used this result, that is 1 minus z minus a
1
divided,
plus x square.
yes, that is 1 minus z to the power minus 1 is nothing but, which is
1
1
plus
plus
z
z
plus
plus x square.
z
So
square.
actually it is nothing but series n running from 0 to infinity z to the power n.
Yes, sir.
So this one becomes, so it is nothing but series n running from 0 to infinity z minus e to the power n divided by w minus e to the power n. So which is nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus e into this one, that is z minus e to the, sorry, series n running from 0 to infinity z minus e to the power n divided by w minus e to the power n dw. Let us take this series outside, then it becomes 1 upon 2 pi I series n running from 0 to infinity integral over the curve gamma to this f of w into z minus a to the power n divided by w minus a into w minus a to the power n. It becomes w minus a to the power n plus 1 dw. As here the integration is with respect to dw, then the term of z will be, it is same as our constant, so it is nothing but 1 upon 2 pi I series n running from 0 to infinity integral over the curve gamma to f of w divided by w minus of a to the power n plus 1 into, sorry, into dw and into z minus a to the power. Okay, so here we get f2 of z as f2 of z as this quantity, that is 1 upon 2 pi I integral, that is this one is nothing but series n running from 0 to infinity 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus of e to the power n plus 1 dw into z minus e to the power n. So that is, it is nothing but series n running from 0 to infinity some an into z minus e to the power n, where now an becomes, where what is an then? An is nothing but 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus of e to the power n plus 1 dw. And this one is nothing but f2 of z. Okay. So here for f2 of z we get an, that is 1 upon 2 pi I integral over the curve gamma to f of w divided by w minus e to the power n plus 1 dw. For here, same as f2, we have to prove that it is also true for f1 also, that is f1 of z is nothing but some series n running from some minus 1 to infinity, or as here f2 of z is nothing but series n running from 0 to infinity. Actually f of z is nothing but f1 of z plus f2 of z. Now series f2 is running from 0 to infinity, then f1 obviously running from minus 1 to minus infinity, then only f of, since already we have given that f of z is nothing but series n running from minus infinity to infinity f, sorry, an into z minus e to the power n. So if we prove that f1 of z is nothing but series n running from minus 1 to minus infinity an z minus e to the power n, and an is nothing but this one, then our result will be true, that is f of z will be equal to f1 of z plus f2 of z. So, okay, so up to f2 of z and an, any doubt?
No, sir.
Okay, now let us consider f1 of z. Consider f1 of z. f1 of z is nothing but minus of 1 upon 2 pi I integral over the curve gamma 1 f of w divided by w minus of z dw, which can be written as 1 upon 2 pi I integral over the curve gamma 1 f of w. As here, from here, that is from w minus z, if we take minus 1 common, then it becomes z minus w, and that minus and this minus get cancelled, so it is nothing but z minus of w dw. Again adjust the term z minus w, that is plus a and minus a, which is nothing but 1 upon 2 pi I integral over the curve gamma 1 f of w divided by z minus of a plus a minus w. Here we will take minus common, then it becomes w minus of a dw. Okay, so which is equal to 1 upon 2 pi I integral over the curve gamma 1 f of w. Now take z minus a common, then it becomes z minus a into 1 minus w minus of a divided by z minus of a dw. So it is nothing but 1 upon 2 pi I integral over the curve gamma 1 f of w divided by z minus of a. Now this one becomes 1 minus w minus a z divided by z minus a raised to minus 1. It means it is nothing but series n running from 0 to infinity w minus a to the power n divided by z minus a to the power some. Here we will use some different notation, that is m running from 0 to infinity w minus a to the power m divided by z minus a to the power m into dw. Okay, so this one is becomes series m running from 0 to infinity 1 upon 2 pi I integral over the curve gamma 1 f of w divided by z minus a to the power m plus 1 into w minus a to the power m dw. Okay. Now, but we require this z minus a to the power z minus a term in numerator. So it becomes series m running from 0 to infinity 1 upon 2 pi I integral over the curve gamma n f of w divided by, let us take this one as in denominator, then it becomes w minus a to the power minus m into z minus a to the power minus of m plus 1 dw. Again here the integration is with respect to w, then this will be same as constant, then it becomes summation m running from 0 to infinity 1 upon 2 pi I integral over the curve gamma n the of w divided by w minus a to the power minus of m dw into z minus of a to the power minus of m plus. So, which implies f1 of z is nothing but sum bn or bm into z minus a to the power minus of m plus, where bm is nothing but, or let us take this one as series m running from 0 to infinity bm z minus a to the power minus of m plus 1, where bm is now becomes 1 upon 2 pi I integral over the curve gamma 1 f of w divided by w minus of a to the power minus of m data. Okay, we can write this one as 1 upon 2 pi I integral over the curve gamma 1 f of w divided by w minus of a to the power minus of m minus 1. As here we have taken minus 1, then you take as it as a plus 1. Okay, so this minus 1 plus 1 can cancel. So actually it is nothing but w minus a to the power minus of m. But by the definition of this one, that is am, is an is nothing but 1 upon 2 pi I integral over the curve gamma 2 f of w divided by w minus a to the power n plus 1 dw. So if this is in this form, then an is, then it is nothing but an. So as here this one is in the form, that is 1 upon 2 pi I integral over the curve gamma 1 f of w upon w minus a to the power minus m minus 1 plus 1 dw. Then what is the value of n here? By
minus
comparing
n minus 1.
minus m minus 1, then what is this value? Then it becomes a of minus of m plus 1, that is a minus m minus 1, which is from star, that about an will be taken as some star. Let us take this one will be some star, and this will be a some equation number 2. Okay, so here f1 of z is nothing but e to minus of m plus 1. Okay, now just put that value here f1 of z, then sorry, this one is not f1 of z, it is a bm, sorry. So put that value of bm in f1 of f1 of z. Here we have to put the value of bm, so it becomes f1 of z is equal to series m running from 0 to infinity. Bm is a minus of m plus 1 into what is z minus a to the power z minus a to the power minus of m plus 1. Okay, now let us write its terms now. Then it is equal to series m is running from 0 to infinity. So put the value of m equal to 0, then it becomes a minus 1 z minus a to the power minus of 0 plus 1, which is minus 1, plus a of m equal to 1, then my 1 plus 1 2 minus of 2 z minus a to the power minus 2 plus up to so on. So actually this series is nothing but series n running from minus 1 to minus of infinity an into z minus a to the power n. Since n is running from minus 1 to infinity, if n equal to minus 1, then it becomes a minus 1 z minus a to the power minus 1, a minus 2 z minus a to the power minus 2, and up to so on. Okay, so f1 of z is nothing but series n running from -1 to -infinity a n z minus a to the power n, and we know that what is a n, where a n is nothing but
1 upon 2 pi I
2 pi I integral over the curve. Now it becomes,
gamma 2
for f1 of z it is gamma 1, f of w divided by w minus z to the power n plus 1 dw. Okay, we have to put this equation 2, sorry, this will be taken as some double star, and this f1 of z as equation number 3. Now we know that f of z is nothing but f2 of z plus f1 of z. So put these values in equation, our f of z. So as f of z equal to f2 of z plus f1 of z. So it is equal to, what is f2 of z? It is nothing but series n running from 0 to infinity an z minus a to the power n plus f1 of z, which is nothing but series -1 to minus infinity an z minus of a to the power n. So total this series is nothing but n running from minus of
minus
infinity
infinity.
plus infinity an z minus a to the power n. And this now f of z is on whole curve gamma. So f now an is nothing but, as gamma is a curve on this f of z, then it is over 1 upon 2 pi I integral over the curve gamma f of w divided by w minus of z to the power n plus 1 dw. Okay, think somewhere it's a small, what is an here? As here we have point A, then we have to take an as w minus a to the power n plus 1. Similarly, here also Vm is nothing but w minus a to the power minus m. Then an is nothing but at point A. So here instead of it we have to take A. An is nothing but w minus f of w divided by w minus a to the power n plus 1. Here also it is, let's write this once again. Since A is a point, 1 upon 2 pi I integral over the curve gamma f of w divided by w minus a to the power n plus 1 dw. Since it is a circle with center at A and having radius will be r on this curve gamma. Since gamma is nothing but z minus a equal to 1. Okay, so here f of z is now becomes series n running from minus infinity to plus infinity a n z minus e to the power n, where a n is nothing but 1 upon 2 pi I integral over the curve gamma f of w divided by w minus e to the power n plus 1 dw. Since for f2 of z it is nothing but integral over the curve gamma 2, for f1 of z it is integral over the curve gamma 1. But addition of these two one is nothing but our f of z, and addition of these two circles is nothing but our circle gamma. Hence here we have to take the integration over the curve gamma. ओके, कुणाला काही डाऊट यामध्ये?
No sir.
सो इथे आपला हा पार्ट आहे, एफ ऑफ जेड इज नथिंग बट दिस वन अँड ए एन इज दिस वन. नाउ वी हॅव टू प्रूव्ह द युनिकनेस ऑफ दिस सिरीज. सो लास्ट पार्ट इट इज नथिंग बट युनिकनेस. Okay, for uniqueness we will take some another series. So let f of z has one more form, which is nothing but series n running from minus of infinity to plus infinity bn into z minus e to the power n is other expansion of f, expansion of a function f at a point a from for any n. Okay, and we have to prove that its uniqueness. It means we have to prove that an is nothing but bn. If we will prove an is nothing but bn, then f of z has a unique expansion. Okay, now we know that what is an. An is nothing but 1 upon 2 pi I integral over the curve gamma f of w divided by w minus a to the power n plus 1 dw. As here we have to use the value of f of z. So here we will convert this a n in terms of z. Then it becomes 1 upon 2 pi r integral over the curve gamma f of z divided by z minus e to the power n plus 1 dz. But f of z has one more form, that is this one. Series n running from minus infinity to infinity bn z minus e to the power n. As here we have already used the n, so this series we will use some j 1 upon 2 pi I integral over the curve gamma. F of z is nothing but series n running from minus infinity to infinity bn into z minus e to the power n. Instead of n we will use here some j running from minus infinity to plus infinity bj into z minus a to the power j divided by our z minus a to the power n plus 1 dj. Okay, so actually it is nothing but series j running from minus infinity to plus infinity 1 upon 2 pi I integral over the curve gamma. Now this bj is constant, then take it as also outside the integration over the curve gamma z minus a to the power j minus of n minus of 1 dj. Okay, which one is nothing but our an, and we have to prove it is equal to our bn. So it is equal to series j running from minus of infinity to plus infinity bj into 1 upon 2 pi I integral over the curve gamma z minus e to the power j minus of n minus of 1 dj. Now here we have to use one property, that is if they suppose there is a circle modulus of z minus equal to r, and here the term z minus e to the power n dz. Now whenever n equal to minus 1, n equal to minus 1, then it is becomes, suppose this will be some curve gamma 1, and now if z equal, sorry, n equal to minus 1, then it becomes z minus a to the power minus 1, it means it is 1 upon z minus of a, and circle is nothing but modulus of z minus a will be equal to r. Then what is its value? What is integral formula, first version, second version? As here power will be 1, n equal to 0, here n equal to 0 na, a equal to
Yes, sir.
a, so it is nothing but 2 pi I into what? Fn of z. Yes,
Yes, sir.
what is the integral formula first version? Which is nothing but Fn of z, but here it is nothing but f0, since n equal to 0. So f0 of z, here f of z will be this one, so which is equal to 2 pi I whenever n equal to minus 1. Okay, now if we take n equal to minus 2, then it becomes integral over the curve gamma 1 z minus a to the power 2, which is equal to 2 pi I into f1 of z, but f of z will be 1, then what is its derivative?
0.
0 into 0, which is equal to 0. म्हणजे हा जर n इक्वल टू -2 झाला तर हा ही व्हॅल्यू 0 येईल. सेम -3 -2 -4 सगळ्यांसाठी 0 येईल, कारण याचं डेरिव्हेटिव्ह वाढत जाईल. -3 च्या बाबतीत डेरिव्हेटिव्ह सेकंड ऑर्डर डेरिव्हेटिव्ह, -3 च्या -4 च्या बाबतीत f3 येईल. म्हणजे as f of z will be equal to 1, then its first order derivative is 0, then the second third must be 0. Then for if n is less than or equal to -2, then this integral value will be equal to 0. Yes, na?
Yes, sir.
Now there is only, we have to check for n equal to 0 and n is greater than or equal to 1. If n equal to 0, then it becomes z minus a to the power 0. Then it is 1 into dz. And we know that Cauchy's theorem. If f is an analytic function, then integration of f will be equal to 0.
Yes, sir.
As 1 is analytic, since 1 is constant, then it must be analytic. As it is analytic, then its integral value will be 0. If z minus a to the power 1, again it is a polynomial. Every polynomial is analytic, then again its integral value will be 0 by Cauchy's theorem. Similarly for z minus a to the power 2, z minus a to the power 3, प्रत्येक बाबतीत ते polynomial. Every polynomial is analytic in its given domain. Therefore, its integral value over that domain will, that is over that region, will be 0, which is from Cauchy's theorem. So integration over modulus of z minus a is equal to r z minus a to the power n dz is equal to 2 pi I whenever n equal to -1 and equal to 0 for all the remaining cases, that is n is not equal to -1. ठीक है?
Yes, sir.
Yes, sir.
Now, but now we have to use this result here, that is z minus a to the power j minus n minus 1. So whenever j minus n minus 1 equal to -1, then only its value will be 2 pi I, otherwise it is 0.
0.
Now tell me when this j minus n minus 1 will be equal to -1. This minus 1 get cancelled, which implies j equal to n.
J is equal to n.
Yes. So whenever j is equal to n, then it becomes series j running, n running from minus infinity to infinity. If j equal to n, which implies an is becomes series n running from minus infinity to plus infinity bn into 1 upon 2 pi I into integration over the curve gamma z minus a to the power n minus of 1 dz, z minus a to the power -1 dz, and which is equal to series n running from minus of infinity to infinity. This value will be 2 pi I. So 1 upon 2 pi I into 2 pi I will be 2 pi I, and it
1.
is series n running from minus infinity to infinity will be n. It is nothing but the same as our an, so which is equal to bn. Okay. So in this case, an is nothing but bn, and for all the remaining cases, the value will be equal to 0. It means it must be equal to an equal to bn. So here, finally, we get an equal to bn, and that is we have to prove, and hence the unit place. Yes, तुम्हाला काही डाऊट आहे?
No, sir.
बाकीच्या केसेस मध्ये तर तो व्हॅल्यू 0 देणार आहे, तिथे an इक्वल टू bnच येईल ऑब्वियस. ठीक आहे, जर डाऊट नसतील, then there is one corollary. Let z equal to a be an isolated singularity of a function f and let f of z is of the form series n running from minus infinity to plus infinity an z minus of a to the power n be its Laurent series expansion. Laurent series expansion in annulus of a with 0 and r. It means modulus of z minus a is greater than 0 and it is strictly less than capital R. And then we have to prove some results. That is the first one. Z equal to a. As here we have given z equal to a be a isolated singularity. Then it is one of the singularity, that is either it is removable, pole, or essential. So z equal to a is a removable singularity. Removable singularity if and only if an equal to 0 for n less equal by minus of. That is, its singular part will be 0. In previous lecture we have what is the singular part of a function f. If its a singular part will be equal to 0, that is the coefficients of 1 upon z minus a to the power n. That one will be equal to 0, then the corresponding isolated singularity will be a removable singularity. Second one, z equal to a is a pole of order m, is a pole of order m if and only if a of minus m equal to 0 and an equal to 0 for n less equal by minus of m plus 1. It means its singular part or principal part contains some finite number of terms. Then only, that is, it means for some m greater than 0, a of minus m will be equal to, sorry, a of minus m is non-zero. It means there are some finite number of terms in its singular part, and for all the remaining cases it is 0. And third one is nothing but z equal to a is an essential singularity. Essential singularity if and only if an is not equal to 0 for infinitely many negative integers. Many negative integers. It means its principal part or singular part contains the infinite number of terms. That is the power 1 upon z minus a to the power n. That is, its coefficients are non-zero. Then the corresponding isolated singularity will be a essential singularity. That is, actually this one is nothing but tells that z equal to a is a removable singularity if its a principal part contains no negative powers of z minus a, contains no term. Second one, that is, it is pole of order m whenever principal part contains some finite number of terms. Principal part contains finite number of terms. Finite number of terms. And last one is nothing but if its principal part contains the infinite number of terms. Principal part contains infinite number of terms. So if we have a power series of a given function, then from that power series itself we say that the function has which type of singularity. Okay, for that we have to first prove this result, then only we will use this method to solve the problems. Okay, now prove first one. Suppose, as we here we have to prove that the if and only statement, that is z equal to a will be a removable singularity if and only if its principal part contains no terms. Okay, so first we will suppose z equal to a be a removable singularity, removable singularity of the function f, of the function f. As f has a removable singularity, then by the definition of, what is the definition of removable singularity?
There exists function such that in deleted neighborhood of that it is analytic.
That is, deleted neighborhood of that point a, the given function will be analytic, which implies there exists some capital R greater than 0 and an analytic function g, analytic function g, which is defined on open ball about a of radius r to a complex number system C, such that g of z becomes f of z. As g of z is analytic, then f of z will be analytic in its deleted neighborhood of a point a. That is, in modulus of z minus a strictly less than r and which is greater than 0. It means it is analytic in the deleted neighborhood of a point a. Now, as G is analytic in open ball about a of radius r, and we know that every analytic function has a power series expansion in its corresponding region. As G is analytic in this region, which implies G has a power series expansion. Therefore, by Taylor's theorem, G of z is nothing but some n running from 0 to infinity bn into z minus e to the power n where modulus of z minus a is less than r, since it is analytic in this region only. But in this region, yeah, g of z is nothing but f of z. So f of z is nothing but series n running from 0 to infinity bn z minus e to the power n in the deleted neighborhood of this point a. Modulus of z minus e is less than. Okay, but already we have given f of z is nothing but series n running from minus infinity to plus infinity a n z minus a to the power n beats the Laurent series expansion in annulus of a with 0 and radius r. It means f of z is equal to annulus of a with radius 0 and r. It is nothing but, if suppose this will be some point a at, then and this will be some radius r. Modulus of z minus a is greater than 0. It means all those points they are, that is z is not equal to a and it is belonging to this region. Z is belonging to annulus of a with 0, annulus of a point a with 0 and r. It means all those points which are belonging to this. Here this point is not equal to our z. It means z is belonging to this region. Okay, and in this region only, that is modulus of z minus a less than r and which is greater than 0, f of z has two power series expansion. In annulus of a with radius 0 and r, it is nothing but f of z is nothing but series n running from minus infinity to infinity bn z minus e to, sorry, an z minus e to the power n, and in that region only f of z is nothing but series n running from 0 to infinity bn z minus e to the power n. But in Laurent series development we have proved that there is a unique expansion for the function f of z. इथं मला f of z साठी दोन वेगळे वेगळे पॉवर सिरीज एक्सपान्शन मिळाले, आणखी तेही सेम रिजन मध्ये. देन बाय युनिकनेस both the series are same.
Yes, sir.
As both the series are same, it means an must be equal to bn, which implies by Laurent series expansion, by uniqueness of Laurent series expansion, uniqueness of Laurent series expansion, an is equal to bn for all n. As an equal to bn for each value of n, then what is the value of an whenever n is less equal by minus 1?
0.
Then an must be equal to 0. Since these two are same, if and only if an will be equal to 0 whenever n is less equal by minus 1. So which implies an is nothing but 0 for all n less equal by minus 1. And that is we have to prove, and hence the required result. First part will be proved. So whenever the given function has a removable singularity at a point z equal to a, then an is equal to 0 for all n equal to minus 1. It means it's a principal part contains no term. Now we have to prove its converse part. So conversely, suppose that an is equal to 0 for all n less equal by minus 1. But we have given the Laurent series expansion, but f of z is equal to series n running from minus infinity to plus infinity z minus a to the power n. Okay, but here an equal to 0 for each value of n less equal by minus 1. Then this f of z becomes series
Summation
n
n
running
equal
from
to 0 to
infinity z minus a to the power n into here's an into z minus a to the power n. Okay, now actually it is nothing but as n is running from 0 to infinity, then a naught z minus a to the power 0, which is 1, plus a1 z minus a plus a2 z minus a square plus up to so on. Now consider limit z tending towards the point a, z minus of a into f of z, which is nothing but a limit z tending towards the point a, z minus of a into this one, that is series n running from 0 to infinity an z minus a to the power n. This will be analytic as a tending towards the point, z tending towards the point a, then it becomes a minus a will be 0, 0 into this will be 0, so which is equal to 0, which implies limit z tending towards the point a, z minus of a into f of z will be equal to 0. Now there is one theorem: if the function f has an isolated singularity at a point z equal to a, then that isolated singularity becomes the removable singularity if and only if limit z tending towards the point a, z minus a into f of z will be equal to 0. So as f of z has an isolated singularity at a point z equal to a, and limit z tending towards the point a, z minus a into f of z will be equal to 0, then we say that
f of z has removable singularity.
f of z has a removable singularity at a point z equal to a. So which implies z equal to a is a removable singularity of a function f. The singularity of function, and hence the yes. Kunal, kahin doubt?
No, sir.